In this tutorial, we will be discussing mechanisms and catalysts. A mechanism is a proposal as to how reactants are converted to products at the molecular level. It's a sequence of events that describe the actual process by which the reactants become products. So we know we're starting here and we're ending here. The mechanism is something that explains what's going on here. All reactants pass through a transition state where there is sufficient energy for activated complex to transcend to the product state. A reaction's rate law is experimentally determined. Rate orders and stoichiometric coefficients are not interchangeable. The chemical equation is a resultant or summary statement. A chemical reaction involves a sequence of elementary steps. So the chemical equation is removing those elementary steps and just telling you the summary of what's happening at the beginning and what's happening at the end, which is why the reaction rates are experimentally determined and you can't just use the stoichiometric coefficients. Intermediates are chemical species found in elementary steps that are used in subsequent mechanism steps. They never appear in the chemical reaction or rate law. So let's talk about multi-step mechanisms. In a multi-step process, one of the steps will be slower than all the others. The overall reaction cannot occur faster than this slowest step. This is called the rate determining step. Think of it as driving on a toll road. Notice at Toll Plaza A, there's a pileup of cars. It's bottlenecking there. And then once you get through it, it's fine. So Toll Plaza A would be the rate determining step. Whereas the next example, the Toll Plaza B is much slower. And so it's the rate determining step. Whereas there doesn't seem to be a backup at all on Toll Plaza A. The molecularity of a process tells how many molecules are involved in the process. For instance, unimolecular only had one item there, whereas bimolecular has to have two things hitting each other to create the product. They are the number of species colliding in a mechanism's elementary step. So once again, unimolecular only has one thing going to the product. Bimolecular, you have two things that have to combine in order to create the product. And termolecular, which is very rare, has to have three things that are hitting each other in order to make the product. The probability of three molecules colliding simultaneously with all the right parameters is very small, so it's very rare. Let's take an example. NO2 plus CO yields NO plus CO2. The rate law for this reaction is found experimentally to be NO2 to the second order. CO is necessary for the reaction to occur. We need it as a reactant, but the rate of the reaction does not depend on its concentration. This suggests that the reaction occurs in two steps. A proposed mechanism for this reaction is NO2 and NO2 are colliding with each other to produce NO3 and NO. Then NO3 comes around and reacts with the CO. Because CO is not in the slow part of the reaction, it's not considered part of the rate determining step. The NO3 intermediate is consumed in the second step. As CO is not involved in the slow rate determining step, it does not appear in the rate law. Also notice, if we look at the final and initial things that are around, we have NO2 and CO yielding NO and CO2. One of those NO2s were canceled and the NO3s were canceled because they're not involved in the overall summary of the reaction. In order to validate, not prove a mechanism, you can never prove a mechanism, you can only validate it. Two conditions must be met. The elementary steps must sum to the overall reaction, and the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. And that's what we were just discussing here. The things that are actually get canceled out are not involved with the overall reaction. And the fact that this is slow and it doesn't contain the CO and it's not in the rate determining step and it's not in the rate law, that tells you that experimentally it also backs it up. Let's change our gears a little bit and start talking about catalysts. Catalysts generally speed up the reaction. They give the reactant molecules a different path to follow with a lower activation energy. There's two kinds of catalysts: homogeneous catalysts and heterogeneous catalysts. Homogeneous catalysts are in the same phase, in other words physical state or something similar to that, as the reactant particles. Catalysts react with one of the reactant molecules to form a more stable activated complex with a lower activation energy. So remember, we had that graph with the starting point and then the activation complex and then the ending point. Well, this is if it was going on normally. If we put a catalyst in there, that activation energy, this complex that it makes, will have a lower activation energy, making that hump a little easier to get over. Sometimes this helps with the start breaking of the bonds. For instance, the ozone, O3, chlorine gas assists with that, with the destruction of that. So homogeneous catalysts are in the same phase. Heterogeneous are in different phases. For instance, this is a solid down here. Heterogeneous catalysts are in the different phase than the reactant particles. It does this by holding on to one of the reactant molecules in proper orientation for the reaction to occur with the collision that takes place. So it helps with the colliding of the molecules. Solid catalytic converters in a car's exhaust system is an example of this. Once again, catalysts are substances that affect the rate of the reaction without being consumed. They work by providing an alternative mechanism for the reaction with a lower activation energy. Notice the lowering of the activation energy here. They are consumed in the early mechanism step, then made again in a later step. So notice that the actual CLO, being the catalyst, chlorine, gets canceled out at the very end. And finally, let's talk about enzymes. Because many of the molecules are large and complex, most biological reactions require catalysts to proceed at a reasonable rate. Protein molecules that catalyze biological reactions are called enzymes. Enzymes work by absorbing the substrate reactant onto an active site that orients the reaction. So here we have an enzyme. The substrate comes in, and then it holds it in place while the reaction occurs, and then the products are made. And that gives you some information about mechanisms and catalysts.